In the previous video, we developed an expression that defines the fully developed thermal profile. What we'd like to do in this video is to take a look at those implications. So this image shows a fully developed thermal profile for some given condition. What we would like to do in the next couple slides are to explore what we mean by a fully developed thermal profile by using a simplified thermal profile. This simplified thermal profile will make it easier to explore the implications of the two cases in which we can consider a thermal profile to be fully developed. Consider the case where we have a tube that is subject to a uniform heat flux. So Qs double prime equals a constant. In this situation, we would expect the fluid to warm as it moves through the tube from stations x1 and increasing up to station x4. In this case, we could start with a wall temperature of Ts1 at section x1, and we would expect, if we continue adding energy in as we move down the tube in the axial direction, the temperature of the wall will increase. And what this would imply is that we would have a thermal profile. The fluid would be cooler near the center, and moving out towards the walls, the temperature would increase. Now, when we move to station 2, we would expect that the temperature would be warmer overall. So, and then moving down to station 3, we would again expect that the fluid will warm again, and likewise when we get to station 4. Now the question is, this implication that the profile, its general shape, is not changing, we need to look at whether or not that's a valid assumption. Newton's law of cooling will apply to this situation, and we can define it as the constant heat flux is equal to the constant convection coefficient, and the temperature difference will be given as Ts minus the mean temperature at any given x location. Now, if we rearrange this, where we divide the constant heat flux by the constant heat transfer coefficient, we get that the temperature difference is likewise a constant. If we take the derivative of this constant, we know that the derivative of a constant is equal to 0, so we get the result that the rate of change, the axial rate of change of the surface temperature, will be identical to the rate of change of the mean temperature. The implication of this is shown in this plot. Now we have an entrance region where we do not expect the thermal profile to be fully developed, but when we reach the fully developed region, we should see that the mean temperature and the surface temperature have the exact same slope, and they are separated by a delta T, which is equal to Ts minus Tm, and that's equal to a constant value of the constant heat flux divided by the constant heat transfer coefficient. Now, if we again look at our situation here, there's a further implication. So if we start with the fact that the rate of change of the temperature, the surface temperature, equals the axial rate of change of the mean temperature, and we apply that to the fully developed thermal profile condition. So if we evaluated this derivative and then substituted in the expression up above, we would end up with a simple result where the local temperature variation, the partial derivative dt dx, is equal to the axial rate of change of the surface temperature, which again is equal to the axial rate of change of the mean temperature. And now what this implies is that since the local temperature is a function of both r and x in the general case, in this situation we find out that that temperature variation does not depend on the radial coordinate. And this being the case, that since the rate of change at any given radial location is the same as any other radial location, we find that this general profile doesn't change as we move down through the tube. So at every delta x, we are essentially adding a set amount of energy into a set amount of fluid, and that is represented by a constant rate of change of the mean temperature for every delta x.